Hello friends, good afternoon and welcome to EduSite Live Lectures. Dear friends, today in Chemical Thermodynamics we will be talking about enthalpy and internal energy changes. To discuss this topic we have with us our subject expert Dr. Shashank Deep. Dr. Shashank Deep is Associate Professor in Department of Chemistry in Indian Institute of Technology, New Delhi. Without further ado, I would like to welcome Sir to our studios and request him to start the lecture. Welcome, sir.
Thank you, Amrita. Today we are going to discuss enthalpy changes, how we can derive enthalpy and internal energy for a process or a chemical change. In thermodynamics, generally you come across several of derivatives, several of equations. The question is, why we want to derive those equations. For example, you will come across del U by del V at constant T, del U by del P at constant T, del H by del P at constant. This kind of quantity you will come across, and we want to derive this in terms of del V by del T at constant P, del V by del P at constant T, or del P by del T at constant P. Now question is, why we want to express these different derivatives in terms of these derivatives. The thing is simple. This quantity del V by del T at constant P, or del V by del P at constant T, or del P by del T at constant V can be measured in a lab. This can also be used to calculate thermodynamic, can be calculated from model equations. So if we know what is the value of these three quantities, we can go back and we can calculate how internal energy changes with volume at constant temperature, or how internal energy changes with pressure at constant temperature. So these are unfamiliar quantities, and we want a relationship between these unfamiliar with familiar quantities, which can be recognized, interpreted, or measured. Del V by del T at constant P is also known as V alpha, where alpha is isothermal compressibility. Del V by del P at constant T is called isothermal your compressibility, and del P by del T at constant V can be expressed in terms of thermal coefficient and isothermal compressibility by using this equation alpha by kappa. So basically what we want to express in thermodynamics is these quantities in terms of alpha and kappa. Now in the last modules we also calculated delta H by delta P at constant T, which is known as isothermal Joule-Thomson coefficient, and that can be given by this equation minus T del V by del T at constant P plus V. And if we express del V by del T at constant P as V alpha, we can write isothermal Joule-Thomson coefficient as minus T V alpha plus V. Similarly, we have another equation which relates del U by del V at constant T with del P by del T at constant V, and this is given by T del P by del T at constant V minus P. So internal energy equal to T alpha by kappa minus P. So this is mu Jt is isothermal Joule-Thomson coefficient, where pi is internal pressure, and these two can be expressed in terms of Tv alpha and Pt alpha and kappa. So now we can express this unfamiliar quantity in terms of alpha which is thermal coefficient, kappa, which is isothermal compressibility, Joule-Thomson coefficient, and your internal pressure. Now, suppose if we want to calculate, we want to know how internal energy changes with pressure at constant temperature, we can use this equation du is equal to del u by del t at constant V dt plus del u by del V at constant T dV. You must remember, I have already told in the last lecture that u is generally written as a function of V and T. One of the important reason for that is we know del u by del T at constant V, and that is nothing but Cv, whereas del u by del V at constant T is your internal pressure. So, basically we express du in terms of your specific heat capacity at constant volume multiplied by dt plus internal pressure multiplied by your dV. So, suppose we want to calculate change in internal energy with pressure, we will simply write del u by del P at constant T. So, now you can see that we are trying to calculate internal energy change with change in pressure at constant temperature. Since temperature is constant, this term, first term is going to be 0. What you are left with is del u by del V at constant T, del V by del P at constant T. Del u by del V at constant T is your internal pressure, and del V by del P at constant T is your minus kappa V. We know that we know that pi is 0 for an ideal gas, internal pressure is 0 since there is no force of attraction or repulsion between an ideal gas. So, pi is 0. In that case, what you end up with is del u by del P at constant T is equal to 0 since pi is equal to 0. So, internal energy of an ideal gas does not change with pressure at constant temperature. Now, we can also calculate change in internal energy with temperature at constant pressure, and the approach is similar, that again we will express du in terms of your heat capacity at constant volume and internal pressure. So, du is equal to del u by del T at constant V dt plus del u by del V at constant T dV. Remember, this is Cv and this is pi. Pi is your internal pressure. So, since we want to calculate change in internal energy with temperature, so we will simply write del u by del T at constant pressure. Now, here the process is carried out at constant pressure. So, this either of these two terms is not going to be 0. So, what you are going to write is del u by del T at constant V, and del T by del T get cancels out. So, this terms is equal to 1. Now, if you go to second term, del u by del V at constant T and del V by del T at constant pressure. So, you can calculate del u by del T at constant pressure. We know that del u by del T at constant volume is Cv plus del u by del V at constant temperature is pi internal pressure, and we can also write del V by del T at constant pressure as V alpha. So, you have equation for del u by del T at constant. Del u by del T at constant pressure will depend on Cv plus pi alpha V. For an ideal gas, we know that pi is equal to 0. So, you can simply put del u by del T at constant P is equal to this Cv, and this term becomes 0 since pi is equal to 0. So, for an ideal gas, you can calculate how internal energy changes with temperature at constant pressure. you can also calculate this for a van der Waals gas, since you know what is the value of pi. Pi is equal to n square A by V square. You just put it here, multiply it, and then you can get CV plus another term. So, it is quite simple once you understand how to calculate, how to start, you can always find out the change in internal energy with temperature at constant pressure or any derivative. It is quite simple to derive an equation. Now, for example, if we want to calculate enthalpy, change in enthalpy with volume at constant temperature. Now, again you must remember that H is generally written as a function of pressure and temperature. Now, it is quite simple why we want to write that, because in that case dH can be written as your, in terms of your del H by del P at constant T, which is nothing but isothermal Joule-Thomson coefficient, while del H by del T at constant P is your Cp. So, now you can express dH in terms of isothermal Joule-Thomson coefficient multiplied by dP plus your del H by del T at constant P, which is Cp multiplied by dt. Now, if we want to calculate change in enthalpy with volume, so what we need to write? Del H by del V at constant T. That is what we are doing here. So, what I am doing is I am just taking derivative of this with respect to volume at constant temperature. If I take constant temperature condition, your dt is going to be 0. So, we are left with only first term, and in that case you can write del H by del V at constant T is equal to del H by del P at constant T multiplied by del P by del V at constant T. Del P by del V at constant T is just inverse of 1 by inverse of del V by del P at constant T, which is nothing but minus V kappa. So, del H by del T at constant V can be expressed as Joule-Thomson coefficient, isothermal Joule-Thomson coefficient divided by minus V into kappa. Similarly, we can calculate change in enthalpy with temperature at constant volume. Again we will start similarly, dH is equal to del H by del P at constant T dP plus del H by del T at constant P dt, which is simply as isothermal Joule-Thomson coefficient multiplied by dP plus Cp dt. Now, since we want to calculate change in enthalpy with temperature, we will write del H by del T at constant V. So, if I write del H by del T at constant V, both term is going to be non-zero, and in that case you can simply write del H by del P at constant T, del P by del T at constant V plus Cp, dt by dt gets cancelled out, and so you are left with Cp. So, this is your general equation, and del H by del P at constant T is generally written as minus mu Cp, and we know that we will later see how to calculate minus mu into Cp, but then you can also we also know that del P by del T at constant V is equal to alpha by kappa. So, now let us see this, that del H by del T at constant V is equal to, just we derived that delta H by delta P at constant T into del P by del T at constant V plus Cp. And from Joule-Thomson coefficient we know that del H by del P at constant T is equal to minus mu Cp del P by del T at constant V is equal to alpha by kappa, So, we can simply write del H by del T at constant V is equal to minus mu Cp alpha by kappa plus Cp, and so you can take out Cp common and you are left with minus mu alpha by kappa plus 1. Now, we will go and see how to calculate del H by del P at constant T is equal to minus mu delta Cp in after few slides. Now, once we know how to calculate del H by del T at constant P, we can calculate what is Cp minus Cv. Cp minus Cv is simply del H by del T at constant P minus del U by del T at constant B. So, Cp is what? Del H by del T at constant P, and Cv is minus del U by del T at constant B. Now, we know that del H by del T at constant P we can write as del U plus Pv by del T by at constant P, since H is equal to U plus Pv, minus del U by del T at constant V. So, what we got if we expand this is del U by del T at constant P plus P del V by del T at constant P minus del U by del T at constant P. We just calculated del U by del T at constant P. We can go back and see that del U by del T at constant P is equal to Cv plus pi alpha V. So, we can simply write del U by del T at constant P is equal to Cv plus pi alpha V plus P, and we know that del V by del T at constant P is simply alpha V. So, you can write this term as P multiplied by alpha V, and this is simply Cv. So, you have minus Cv. Now, this Cv cancels out. What you are left with is pi alpha V plus P alpha V. So, we can take out alpha V as a common. We are left with pi plus P alpha V, where pi is internal pressure. Internal pressure is given as T del P by del T at constant V minus P, and plus P from this multiplied by alpha V. Pp cancels out. What we are left with is equal to T del P by del T at constant V into alpha V, and that is nothing but alpha square Vt by kappa. So, this is the general equation for Cp and Cv. This can be applied for both ideal gas or a real gas. Real gas can be van der Waals gas or any other gas which follow another model. Now, let us see if we have an ideal gas, what will be the value of Cp minus Cv. We just know that Cp minus Cv is equal to alpha square Vt divided by kappa. For an ideal gas, we know that V is equal to RT by P. We can calculate alpha, which is simply equal to 1 by T. If we calculate kappa, it is equal to 1 by P. And now, if you place these values here, then we can simply get Cp minus Cv, and what we will find out is Cp minus Cv is equal to Nr. So, from a general equation, we can calculate what is the value of Cp minus Cv for an ideal gas. So, you must remember this, that it is easy to calculate your Cp minus Cv for a reaction for an ideal gas using this equation. This equation can also be used to calculate Cp minus Cv for a van der Waals gas. In that case, alpha by kappa is equal to simply R by V minus V, and V alpha is simply equal to R by divided by P minus A by V square plus 2AB by VQ. These are simple derivatives. this is your derivative of V with respect to your T, while alpha by kappa is del P by del T at constant V. So, we can calculate these two things easily from a van der Waals gas, and so we can get Cp minus Cv is equal to R divided by 1 minus 2A RT Vq V minus V square. So, whenever you have been given a gas following some model, you can use this equation to calculate Cp minus Cv for that gas. For ideal gas, this is equal to R, but not for a real gas. So, Cp minus Cv is equal to R only for ideal gas. For a van der Waals gas, Cp minus Cv is R divided by this whole factor. There is another way to get del H by del P at constant T, which is isothermal Joule-Thomson coefficient. For that, what we apply is what is known as Euler's cyclic rule. So, suppose there are three variables, then state variables, then we can apply Euler's cyclic rule. It does not matter whether we go in a cyclic direction, in a clockwise direction, or your counterclockwise, anti-clockwise direction. We can simply start, suppose we start from H, then we can write del H by del P at constant T, del P by del T at constant H, del H del T by del H at constant P is equal to minus 1. This can be written for any three state variables, and this is quite often used in thermodynamics to derive equations. So, if we want to calculate del H by del P at constant T, we can simply write minus del T by del P at constant H. So, basically what we did is we took this term to this side and just write 1 divided by del P by del T at constant H as del T by del P at constant H, and then del H by del T at constant P. We know that this term is P, whereas delta T by delta P at constant H is known as Joule-Thomson coefficient. This was the equation which we used to derive the first del H by del T at constant P. This mu is called Joule-Thomson coefficient, and one of the important point about this mu is that if it is easier to measure temperature change when we change the pressure, but most difficult part is how to apply constant enthalpy conditions, and that is the place where your Joule-Thomson has given his contribution. So, he told how to impose the constraint of constant enthalpy. Now, see, this is a cylinder which is your adiabatic, which has adiabatic wall. So, heat cannot go from this side to that side. They have a partition which has a small hole here, and there are two your pistons on both sides of the partition. Now, suppose this is your initial condition. So, all the gases are in this chamber which has pressure Pi, Vi, Ti, and there is no gas here. Now, suppose they are compressed so that they go to all the gases pass to second chamber with volume Pf, Vf, Tf. Now, if we want to calculate work done in this, we can do that. So, in the first case, you can see that your final pressure is your 0. So, Pi Vi minus Pf Vf. So, this is your work done your final pressure is Pf Vf, and so this side it is 0. So, you are going from Pi Vi to, in this chamber, Pi Vi to 0. So, in that case this chamber work done is Pi Vi. In this chamber you are going from 0 to Pf Vf Tf, and so your work done is minus Pf Vf. Since this is an adiabatic process, your walls are adiabatic, so heat will not flow out, and in that case Q is equal to 0. So, you can calculate internal energy change, which is UF minus Ui. UF minus Ui should be equal to W, since your Q is equal to 0 and W in this case is Pi Vi minus Pf Vf. So, you can simply write del U is equal to Pi Vi minus Pf Vf. So, delta U is equal to Uf minus Ui. So, Uf, you take this term this side, you will get a plus sign. So, Uf plus Pf Vf is equal to Ui plus Pi Vi. So, now you see that final enthalpy is equal to initial enthalpy, and thus they are able to, Joule-Thomson were able to impose the constraint of constant enthalpy. Once you impose the constraint of constant enthalpy, you can always calculate, you can always know what is the temperature change with your pressure at constant enthalpy. We already proved that del H by del P at constant T is equal to minus mu Cp. This is Joule-Thomson coefficient. This is isothermal Joule-Thomson coefficient, where mu is your Joule-Thomson coefficient. So, mu is equal to simply minus del H by del P at constant T Cp. So, mu is equal to del T by del P at constant H is equal to minus del H by del P at constant H is equal to this quantity divided by C. We know that this quantity del H by del P at constant T is equal to 0 for ideal gas. So, mu is also 0. So, but for a real gas this is not equal to 0. So, real gas have non-zero Joule-Thomson coefficient. Delta P, this is expansion experiment. So, delta P is always going to be negative. So, a positive mu corresponds to cooling on expansion. So, positive, and if delta P is negative, it can only happen when delta T is negative. So, negative divided by negative is a positive quantity. So, a positive mu corresponds to cooling on expansion, whereas a negative mu corresponds to warming. Using the earlier equation, the relationship between mu Jt and your mu, we can simply mu Jt we can calculate 1 by Cp 2 is equal to, mu Jt is equal to 1 by Cp 2a by RT minus 3a Bp R square T square minus B, and under the condition of low pressure and high temperature, we can neglect this higher order term, and you are left with 1 by Cp 2a by RT minus B. Now, from mu Jt you can always calculate back mu, which is simply mu is equal to mu Jt minus mu Jt by Cp. Now, you see this here, your T versus P. So, this is an expansion experiment, and this sign of, so you can see that initially there is increase in the value of temperature with increase in pressure, whereas there is a decrease in the temperature with pressure. The temperature corresponding to the boundary at a given pressure is called inversion temperature of the gas at that pressure. In this, since mu is equal to positive, in this region the cooling will be experienced, while in this region your heating will be or warming will be observed. and this point is called inversion temperature. So, any gas has two different inversion temperature, upper inversion temperature and lower inversion temperature. This is again from for the nitrogen. For hydrogen, this curve shifts, and this is at you can see it below. For helium, it will again go below. So, enthalpy changes in a isothermal process. H is equal to function of P and T. So, del H is del H by del P at constant T dP plus del H by del T at constant P dt. So, del H by del P at constant T dP plus Cp dt. For an ideal gas, we know del H by del P at constant T is equal to 0. So, dH is equal to Cp dt, and thus for an isothermal process, dH is equal to 0. For a real gas, we know that your this mu Jt is not going to be 0, but since this is isothermal process, Cp dt is 0. So, dH is simply written as mu Jt dP. A simple calculation: calculate maximum work done when 2 mole of an ideal gas expands isothermally and reversibly from a volume of 2 liter to 4 liter at 300 K. What is the change in internal energy and heat absorbed and evolved in the process? The way to approach this problem is, first take a note that this is for ideal gas, process is reversible and isothermal. So, we will start with W is minus P external dV. Since this is a reversible process, P external is equal to P, that is given by nRT by V when the gas is ideal, and if it is isothermal, you can take this nRT out. So, work done is minus nRT V1 to V2 minus 1 by V dV. du, you always start with this equation Cv dt plus pi dV. That becomes Cv dt if you have ideal gas, and since this is isothermal process, du is equal to 0. So, dq can be calculated from the work done, where dq is minus dw. Thank you very much. Okay, so in this module, we are going to discuss thermochemistry. How delta H can be used in the thermodynamics. If you take any reaction or any physical process, that is always accompanied by absorption or release of heat from the system or by the system. This heat evolved or absorbed can be measured by measuring heat at constant pressure. You know that heat at constant pressure is called enthalpy. So, when we measure heat at constant pressure, we are basically measuring enthalpy. So, there are two types of processes, one in which heat is released from system to the surrounding. When it happens, what we will find out is when you touch the reaction vessel, you will feel warm. For example, your H2O gas, well, when you goes to liquid form of H2O, it is always accompanied by heat release. Whereas endothermic process is a process in which heat is absorbed. So, when you carry out the opposite process, so when you are trying to go from liquid to gas, in that case you have to supply heat, or you want to go from solid to liquid, you have to apply heat. Opposite, you have the heat will be released, and that process will be exothermic. So, heat released or heat absorbed is basically equal to enthalpy of the reaction, because mostly reactions takes place at constant pressure. So, change in enthalpy is nothing but change in basically enthalpy, total enthalpy of product minus total enthalpy of the reactant. So, delta H is H product minus H reactant. For endothermic reaction, generally H product is greater than H reactant. So, delta H for the process is greater than 0. For exothermic process, H product is less than H reactant. So, delta H is less than 0. Now, what is a physical process? When you apply heat to water in liquid form, in that case it goes to a gaseous form. There is no reaction, only phase is changing, and that is called your physical process. And for this heat of vaporization, the heat which is supplied is equal to 44 kilojoule per mole. For the reverse process, means when you are trying to go from gaseous form to liquid form, your delta H is equal to going to be minus 44 kilojoule per mole. For reverse process, always delta H is going to be the negative of the forward reaction. So, reaction is exothermic in this case, while reaction is endothermic in this case. So, for vaporization, reaction is endothermic, whereas from gas to liquid, your reaction is exothermic. A chemical process, for example, C graphite plus O2 gas going to CO2 gas, your 394 kilojoule of heat is released, and so the reaction is exothermic. Delta H is minus 394 kilojoule per mole. What are the examples of different exothermic chemical processes? Any combustion reaction, so when you are trying to burn anything, that is going to be exothermic process. Rusting of iron, or you can say oxidation of iron, which is generally used in chemical hot pack, and so that is an exothermic reaction. A reaction between water and calcium chloride is also a exothermic process, whereas a reaction between sodium and chlorine to make sodium chloride is also an exothermic process. Exothermic physical process, so where there is no reactions, only phase is changing or some other things is happening. For example, if you dissolve laundry detergent in water, if you try to crystallize sodium acetate, if you freeze water into ice, and snow forming inside clouds, these are examples of exothermic physical processes. Reaction also happens with absorption of heat, and those reactions are called endothermic chemical reactions. For example, if you are dissolving ammonium chloride in water, that is an endothermic reaction. If you mix water with ammonium nitrate, again you will feel cold since reaction is endothermic, and so it is used in cold pack. Reaction of barium hydroxide octahydrate crystal with dry ammonium chloride, reaction of thionyl chloride with cobalt 2 sulfate heptide. There are several examples, few of the examples I have mentioned here. So, there are physical process also which can be endothermic. For example, if ice melts, any solid salt melts when you evaporate liquid water, and if you convert frost to water vapor. For thermochemical equations, when you write a thermochemical equations, you must mention the physical states of all reactants and products. For example, take this process, water in solid form going to water in liquid form. So, in parenthesis you must write what is the physical state of water. When it is a reactant, you must write what is the physical state of water when it is a liquid, and for that delta is equal to 6.01 kilojoule. Now, if you take water in liquid form and try to convert water into gaseous form, delta H is equal to 44 kilojoule. So, you can see that both reaction involves water. So, it is quite important to write the physical states, since for two different physical states going to two different physical states, delta H can be different. So, it is must that you must specify the physical states of all reactants and products. So, H2O solid to H2O liquid, delta H is equal to 6.01 kilojoule. If we reverse the reaction, if we go from H2O liquid to H2O solid, now you can see delta H has different signs. It is now minus 6.01 kilojoule. Now, the second important thing to remember is enthalpy change for X molecule of reactant is X times the enthalpy change for 1 mole of reactant. So, if I just multiply this by 2, so for a reaction where 2 molecule of water in solid form is going to 2 molecule of water in liquid form, you can calculate delta H, and in this case it will be equal to 2 multiplied by 6.01, which is 12 kilojoule. Now, there are different kind of enthalpies. One important enthalpy term is standard enthalpy of formation, which is denoted by delta H naught F. Naught is generally for a standard form, F is formation. This is equal to enthalpy change of the system when 1 mole of a compound is formed from its constituent elements. Now, for the standard enthalpy of formation of any element in its most stable form is 0. For example, delta H formation for oxygen in a gaseous state is equal to 0, because oxygen generally exists as in O2 form. Delta HF naught for ozone is equal to 142 kilojoule per mole. Carbon most stable form is graphite, and for this the standard enthalpy of formation is 0, whereas for diamond it is 1.90 kilojoule per mole. So, you can see this is the most stable form of carbon, whereas oxygen is most stable form of oxygen. For both of these, your standard enthalpy of formation is 0, not for the less stable compound. What is the standard state condition? Temperature is your 25 degrees Celsius or 298 Kelvin, pressure is 1 atmosphere, and element should be in its stable state. For example, oxygen can exist as atomic oxygen, O2 in gaseous form, O2 in liquid form, O3 in gaseous form. In all these, this is the most stable form, and so for this this is a standard condition. Between carbon diamond and carbon graphite, this is the most stable form of graphite, and so its standard enthalpy of formation is 0. Now we can calculate a standard enthalpy of formation for any other molecule. For example, if we want to calculate CO2 enthalpy of formation per CO2 gas, we can calculate from this equation, C graphite plus half O2 gas giving you CO gas, H naught is equal to minus 26.42 kilocal. So these two equations is given. First there is a formation of carbon monoxide, in the second equation there is formation of carbon dioxide in gaseous form, and we want to calculate the enthalpy of formation of CO2, which corresponds to this reaction C graphite plus O2 gas going to CO2 gas. The way we can do it is we simply add these two. When we add these two, this CO gas cancels out, and half O2 plus half O2 is one molecule of oxygen. So combined equation is C graphite plus O2 gas, CO2 gas. So we just add these two equations, we can get the your desired equation, and in this case delta H will be simply the sum of these two quantities, which is minus 94.13. Okay, so there is one very important law in thermochemistry, which is Hess law. Here this tells you that enthalpy change of a reaction is same whether the reaction takes place in one step or in a series of steps, or simply it is independent of root. Simply it is independent of root. So this can be used to calculate enthalpy change of an unknown reaction if we know enthalpy change for a series of reaction which sum is equal to the reaction where we want to calculate enthalpy change. So standard enthalpy of reaction is enthalpy of reaction carried out at 1 atmosphere, and if you have A molecule of A plus B molecule of B giving C molecule of C plus D molecule of D, in this case delta H of reaction can be simply written as C multiplied by delta H formation for this C, D multiplied by delta H formation of D. So this is for the product, and now you subtract with the reactant A molecule multiplied by delta H formation of A plus B multiplied by delta H formation of B. So it is simply N multiplied by delta H of formation for products minus M multiplied by delta H formation of reactant. What is enthalpy of combustion? It is the enthalpy change when 1 mole of substance is completely burnt in excess of air. For example, if you are trying to write combustion of butane, it is C4H10, a gaseous form, plus 6.5 O2 gas gives you 4 CO2 gas plus 5 H2O. So delta H formation for C4H10, we know that it is 2878.7 kilojoule per mole. Oxygen, since it is in the most stable state, its delta H formation is going to be 0. CO2 delta H formation is minus 394 kilojoule per mole. For water in liquid form, it is minus 286 kilojoule per mole. So, we can calculate delta H of reaction, and the way we calculate is, now first we multiply this minus 394 by 4 minus, and then add with minus 286 into 5, and then you have to subtract by simply minus 2878. So, simply delta H of reaction will be 4 delta H formation of CO2 plus 5 multiplied by delta H formation of H2O in liquid form minus delta H formation for C4H10. Okay. So, now if we know enthalpy of reaction at one temperature, the question is whether we can calculate the enthalpy of reaction at another temperature. That can be done using Kirchhoff's law. So, enthalpy of reaction at 25 degrees Celsius, we just showed that it can be calculated from the standard enthalpy of formation, and once we know the enthalpy of reaction at 25 degrees Celsius, we can calculate enthalpy at other temperature using Kirchhoff's law. So, what is Kirchhoff's law? We know that delta H of reaction is H product minus H reactant. So, delta H of reaction divided by dt is equal to dH product by dt minus dH reactant by dt. So, what is dH by dt? We have already seen that this is Cp. At constant pressure, this will be equal to Cp. So, in that case, we can simply write Cp product minus Cp reactant. Now, we can bring this dt this side, and we can calculate delta H at two different temperature. The way we do is simply you bring dt this side, and then we integrate it between delta H1 to delta H2, and here integration can be from T1 to T2. So, d delta H and delta Cp dt T1 to T2, and if you integrate this, we can get delta H2 minus delta H1 is equal to your delta Cp dt from T1 to T2. So, delta H2 is delta H1 plus delta Cp dt, and if suppose delta Cp is independent of temperature, you can take this out, and delta H2 is simply delta H1 plus delta Cp T2 minus T1. Now, what happens when a reaction is taking place? Some bonds are broken and some bonds are formed. If bonds are broken, you can look at the bonds. If you want to break a bond, you need to supply force, which is generally used to overcome the attractive force. So, bond breaking is always an endothermic process. This bond can be any kind of bond. It may be a covalent bond or electrostatic or van der Waals bond. On the other hand, when there is a formation of bond, energy is released, and thus bond making is an exothermic process. Breaking or making the same chemical bond will require the same energy to be put in or released. The enthalpy chain required to break a particular bond in 1 mole of gaseous molecule is your bond energy. So, for example, if you have a hydrogen molecule and if you want to break that bond, if you do that, to make 2 atoms of hydrogen, the heat release is 436.4 kilojoule, and this is your bond energy for your HH bond. In HCl, again you have 431.9 kilojoule if you try to break this bond. In oxygen gas, if you break the OO bond, your enthalpy will be 498.7 kilojoule. So bond energy of OO bond is your 498.7 kilojoule. You can determine heat of formation using the bond energy. For example, if you take the case 2 carbon gas plus 6 S2 gas giving C2H6 gas. In this case, delta H is equal to sigma bond energy of reactant minus sigma of bond energy of product. Now you see that for C gas, there is no, when it goes to product, number of bond broken is 0, bond energy 0, energy change 0. For HH, you need to break this bond. There are 6 such kind of bonds, so 1 into 6, number of bonds broken 1 into 6. If suppose bond energy is BEHH, then energy change is 6 BEHH. Types of bond formed is your 1 CC bond, and if bond energy is BECC, enthalpy change will be BECC. And so you can see that there is 1 CC bond formation, 6 CH bond formation, and that will be equal to if this is BECH, then 6 BECH. Now you see that delta H of the reaction, delta H of formation of C2H6 in gaseous state will be equal to delta H BE bond energy of 1 CC bond plus 6 bond energy of CH bond minus bond energy of HH bond. So now you can see that we can calculate your heat of formation if we know the bond energy of each bonds. Thank you.
On that note, I would like to thank sir for this very interesting discussion, and thank you dear friends for watching our show. Stay tuned and keep watching. Thank you.